In the world of aviation, the phrase, "if it's Boeing, I'm not going," has stuck around because it reflects three major pain points that travelers and airlines alike have dealt with for decades. These problems include shaken trust due to safety incidents, schedules thrown off by long and unpredictable maintenance holds, and the loud, disruptive noise of turboprop aircraft that make early morning or late evening departures unpleasant and often restricted. These long-standing issues form the backdrop against which Elon Musk's ambitious vision for Tesla's 2026 super-electric plane emerges, a project designed not just to challenge the dominance of legacy manufacturers like Boeing, but to completely redefine short-haul air travel. Musk has hinted for years that the truly exciting frontier lies in electric vertical takeoff and landing supersonic jets. This aircraft is positioned not as a niche concept, but as a practical game changer, one that directly addresses the inefficiencies and irritations of regional flying, and may well fuel the decline of traditional aircraft in the short-haul sector. Tesla's proposed electric plane is built around promises that are both tightly focused and grounded in practicality. Rather than competing with massive long-haul jets, it envisions a compact 4 to 12-seat cabin designed for community routes of up to 500 miles. Turnarounds are streamlined through modular batteries that can be swapped in just 15 minutes, keeping planes in the air instead of waiting idly on the tarmac. Quiet electric motors eliminate the noise pollution of conventional turboprops, reopening valuable early morning and late night departure slots at smaller airports. Fewer moving parts mean fewer breakdowns and far less hangar drama, replacing the current model of inconsistent reliability with a factory-like consistency. This blend of efficiency, reduced noise, and simplicity could completely transform how short-haul air travel is scheduled, operated, and experienced. For everyday travelers, the Tesla super-electric plane offers a host of thoughtful design improvements that address frustrations, both big and small. The passenger experience begins with the cabin layout. Tesla's design favors compact seating arrangements, either 1-to-1 or 2-to-1, which creates aisles in the range of 18 to 20 inches. This means passengers can move with greater ease, reducing the awkward bumping of elbows or shoulders that plague many small regional flights. Boarding is simplified by a large low door paired with a step height that allows passengers to walk in with one hand free instead of treating entry like a physical workout. That same 50 by 50-inch door is large enough to accommodate standard cargo tubs or even medical stretchers, which measure around 22 to 24 inches wide. The aircraft can therefore shift quickly between passenger service, cargo hauling, or emergency medical operations without the need for specialized equipment. Quick-release seat rails make such reconfigurations possible in minutes, turning the plane into a versatile platform rather than a single-use vehicle. Durability is another central theme in the design. Short-haul aircraft typically log a high number of cycles, which accelerates wear from fatigue and corrosion. To counter this, Tesla's engineers propose a careful balance: corrosion-resistant aluminum for the main structural elements and lightweight composite panels for fairing. Areas subject to high stress would receive double plating, while seams are deliberately placed where mechanics can see them during inspections. Every recurring inspection point is positioned for access without the need to tear apart the interior. This means maintenance is faster, cheaper, and more consistent. Even the seats and restraint anchors are built to meet dynamic crash standards rather than simple pull tests, ensuring that passengers are better protected in the event of a rough landing. Now, the ultimate goal is an aircraft with a service life counted in tens of thousands of flight hours before major structural work is required. The external design also contributes to efficiency and comfort. Noise reduction begins with aerodynamics before the engines are even switched on. Clean wing surfaces with smooth leading edges combined with modern wingtip treatments reduce induced drag, which in turn extends range within the aircraft's limited battery budget. These aerodynamic choices also soften the pressure pulses passengers and bystanders hear during approach and landing. Enclosed or faired landing gear reduces the whistling and rumble often associated with turboprop arrivals. Propellers are sized carefully so their tips remain below high subsonic speeds, avoiding the sharp, high-frequency tones that carry across neighborhoods. When paired with quiet electric motors, the overall noise profile becomes so low that airports can approve more early morning and late evening slots, something almost impossible with current turboprop fleets. This directly improves schedule reliability and utilization by allowing aircraft to operate at times people actually want to travel. Underneath the sleek design, the aircraft is engineered with serviceability at its core. High-use components such as inverters, motor controllers, battery management electronics, avionics, and the environmental pack are all housed behind easily accessible panels and treated as line-replaceable units. Each unit uses keyed, color-coded connectors, allowing a two-person ground crew to swap out a faulty module in as little as 5 to 10 minutes using standard tools. Panels can be opened without removing seats, and fasteners are standardized across the airframe. Each component even carries a QR code linking it to digital manuals and its parts history. This modular philosophy ensures that small problems do not escalate into day-long maintenance delays, keeping aircraft in service and passengers moving. Battery modules themselves are designed with guiding rails, latches, and safety interlocks so that a full swap can be completed within Tesla's target of 15 minutes. This schedule consistency is revolutionary compared to the unpredictability of current regional aircraft operations. Tesla's super electric plane also reshapes short-haul flight schedules by making two key numbers predictable: a guaranteed 15-minute turnaround and a range of up to 500 miles. These are not theoretical figures, but operational rules built into the design. On the ground, the 15-minute routine includes parking, unloading and reloading, swapping preconditioned batteries, running automated checks, and pushing back. With only 4 to 12 passengers, boarding and deplaning take no more than 3 minutes each. Baggage handling runs in parallel, and the battery swap takes around 6 to 8 minutes, leaving the final minutes for checks. This is far tighter than the 25 to 35-minute turnarounds typical of small regional planes, meaning every cycle adds efficiency rather than bleeding time. The effect on daily schedules is profound. On routes of 250 miles or less, a full flight cycle, including taxiing, flying, and turnaround, fits into 60 to 90 minutes. This allows a single aircraft to fly 10 to 16 legs per day, depending on demand and operating hours. On longer routes of 250 to 500 miles, flight time increases, but the same 15-minute ground routine ensures that 6 to 10 legs are still achievable. The consistency of these short ground stops keeps the timetable from unraveling, a constant headache for airlines today. For passengers, this translates into real door-to-door time savings. A trip that might take 3 to 5 hours by car is compressed into 90 minutes to 2 hours by air, including check-in and transfers, because the aircraft operates from smaller, underutilized community airports with short taxi paths and minimal queues. Noise reductions unlock even more scheduling flexibility. With electric motors and a cleaner acoustic footprint, Tesla's plane can gain approval for early morning and late-night slots at community airports. This means flights can be scheduled at times people actually want to travel, while airlines benefit from increased aircraft utilization and improved on-time performance. Operating costs are also dramatically reduced. Direct-drive electric motors avoid the complexity of gearboxes, meaning fewer moving parts, calmer vibration, and simpler inspections. With efficiencies of 90 to 95%, most of the battery's stored energy is converted to thrust rather than wasted as heat. Multiple independent motors add redundancy, ensuring that a single failure does not ground the plane or wreck an airline's timetable. Battery technology underpins the cost savings. Modular packs weighing between 1.7 and 2.8 metric tons store 600 to 900 kilowatt hours of energy, equivalent to 6 to 9 long-range electric cars. Managed within optimal temperature ranges by liquid cooling and smart battery management systems, these packs can deliver 1,500 to 2,000 cycles, meaning years of reliable daily service. The ability to swap preconditioned packs in minutes during the day and recharge them overnight during off-peak electricity hours keeps costs low and schedules tight. At typical U.S. electricity prices, direct energy costs per flight hour range from just $24 to $54, compared to $225 to $315 for turboprops burning jet fuel. This favorable cost structure enables lower fares without sacrificing profitability. For example, on a 500-mile leg, a 10-seat Tesla plane operating at an 85% load factor carries 9 paying passengers. Cruise consumes about 650 kilowatt hours, costing around $78 at off-peak rates. With small airport landing fees of $20 to $40 and maintenance costs of $35 to $55, the total direct cost per flight is around $133 to $173. This translates to about $15 to $19 per passenger before crew and overhead, making ticket prices of $79 to $139 economically sustainable while still leaving room for promotional fares. The implications for legacy aircraft manufacturers like Boeing are serious. As passengers grow accustomed to fast, quiet, and fairly priced regional flights, airlines will follow the economics. Within 1 to 2 years of steady service, total ownership costs for electric planes could be 25 to 30% lower than conventional aircraft. This creates a strong financial incentive for airlines to tilt new capacity toward electric aircraft first. Routes of up to 500 miles, which form the bread and butter of regional aviation, would naturally shift away from noisy, maintenance-heavy turboprops to cleaner, more reliable electric alternatives. This is why analysts see Tesla's super electric plane not merely as an innovation, but as the potential beginning of the end for Boeing's dominance in short-haul markets. Ultimately, short-haul air travel is about to feel very different. With 15-minute turnarounds up to 500-mile range, quiet operations from community airports, and significantly lower cost, Tesla's entry into aviation could put small towns back on the air travel map. It offers passengers a smoother, quieter, and more affordable experience while giving airlines tighter schedules and better economics. If Tesla delivers on this vision, the ripple effects will be felt not only by travelers but across the entire aviation industry.